Welcome to our last lecture in Chapter 7. This is on 7.5, Algebraically Defined Vectors and the Dot Product. This is actually kind of cool because it makes solving for resultant vectors a lot simpler if we use the Cartesian system or the rectangular system. And so we're going to look at how we can use the XY grid, XY values to solve for vectors. And then we're even going to learn how to use our TI-84 calculators to solve some of these problems as well. Okay. A vector with its initial position at the origin is called a position vector. And here you can see vector u. A position vector with its endpoint at the point x equals a and y equals b, which you can see here, is written as vector AB. And you can see here instead of parentheses we have these basically parentheses that look slightly like arrows. Okay, so we can write this as vector AB using these special pointed parentheses. The numbers A and B are the horizontal and vertical component respectively of V. We understand that A is the X value, so it's the horizontal value, the horizon, and B is the vertical component, or the Y value, or the height, if you will, or something like that. Okay. The positive angle, notice that positive angle between the x-axis and the position vector is the direction angle of the vector, okay? And you can see that here. The magnitude, which is the length of the vector, is given by u, the magnitude of u, the absolute value of u equals the square root of a squared plus b squared. This is simple, you know this. This is simply the Pythagorean theorem. Since we're doing it, we have a right triangle, a squared plus b squared equals c squared, or in this case, u squared, so u equals the square root of the sum of those squares. Nothing new, nothing earth-shattering, not rocket science by any means. Actually, it might be a little bit of rocket science, but you're learning. So now you can tell people you know a little bit of rocket science, because certainly bearings and wind speed, etc., is definitely part of rocket science. All right, sorry, I digress. And finally, the angle. We know that the tangent of an angle of a right triangle is equal to the opposite over the adjacent sides. So here we can find the tangent of that angle equals b over a, and if we wanted to find the angle, we can use the inverse tangent function. Okay? This notation of vectors using x and y values is called rectangular. Okay, these are the rectangular form of vector notation. Okay, when we talk just in terms of magnitude and angles, that's called the polar form. Okay, polar form. All right, and that'll come into play with our calculator in just a minute or so. All right, find the magnitude and direction angle for vector u equals 3, negative 2. So the first thing you want to do is draw this. Just graph it. Where would 3, negative 2 be on a Cartesian, on a graph? So x is 3, y is negative 2, so go ahead and draw that. Okay? You can see it here in quadrant 4. And again, remember our angle measure is theta, is the positive direction from the x-axis. Okay, so we're going to have an angle greater than 270. All right. The magnitude of our vector is simply the square root of x squared plus y squared. In this case, it's the square root of 13, the square root of 3 squared plus negative 2 squared. Okay. Our directional angle, tangent of theta equals b over a, or y over x. Is that right? Yeah, y over x. Sorry, I went blank there. negative 2 over 3, and you can think of it as this little triangle here, right? The tangent of theta, we can use the reference theta here, is opposite y, negative 2 over x 3. So theta equals, if we do our inverse tangent, notice we're getting a negative angle, but our theta is the positive angle. So what it's giving us is this little angle between the vector and the x-axis. And so of course we add 360 to it to get back to the coterminal angle, which is the positive angle. All right, and we're done for that problem. Now, if you look on your calculator and you look, sorry, let me pull up my calculator and make sure I get this right. And you look under the angle function, okay? The angle function is, it's on the apps button. It's the second function on the apps button, which is directly to the right of the math button, okay? And you'll see angle above that. If you hit second and that apps button, you'll get the angle apps, and you'll see number 5 is R to PR. This is rectangular notation to polar, okay? To polar, all right? And so if you plug in the x and y coordinates of your vector, given in rectangular format or in xy format, it will convert this to the magnitude, R to PR, okay? This will give you the magnitude of your vector. And you can see that that matches the square root of 13. That's why that middle one is there, just so you can see that it's identical. So your angle app, R to PR, will give you the magnitude of your vector. If you go down to number 6 on that angle app menu, you'll see R to P theta, and this converts from rectangular XY grid to polar format, which is magnitude and angle. Again, you plug in your X and Y value, and you get the angle there. Of course, again, we've got the negative 33.7, and that's the smaller angle. We would need to add 360 to this to get the correct angle, the correct positive coterminal angle. Remember that polar notation is magnitude and positive angle, okay? The horizontal and vertical components respectively, if you're given the magnitude and angle of a vector, you can find the x and y value. Again, this is nothing new. This is really just using cosine equals adjacent over hypotenuse and sine equals opposite over hypotenuse. And we're just, now of course the opposite and the adjacent are the x and y values. Okay, so you can see here the x value is u, the magnitude, times the cosine of theta. And we knew that. We knew that from, looking at throughout this course, thinking of cosine as x and sine as y. So this isn't totally new. It's a new kind of notation, but it uses the knowledge that we've had throughout the course. Cosine is the x value, sine is the y value, and to find those, we simply multiply the cosine of the angle times the magnitude or the sine of the angle. All right. Vector W has a magnitude of 25 and a directional angle of 41.7. Find the horizontal and vertical components. This is a very simple problem. You want to hit pause, fine, do that. It's always a good idea if you know what you're doing, if we've had a second problem, to go ahead and hit pause to try it yourself and see if you can get it, because you're going to learn more that way and you're going to master the material quicker. I know you want to do it quicker. All right. So for the x value, it's the magnitude times cosine theta, or 18.7. For the y value, it's the magnitude times the sine of theta, which gives us 16.6. So we can state this vector w in terms of x and y, or 18.6 comma 16.6, using the special pointed parentheses. And again, if you wanted to list them separately, the horizontal component is the x value, the vertical component is the y value, and you can know that just by looking at any graph, right? X is on the horizon. X is the horizon where the sun rises and sets. It's that long horizontal line. And if you go back to your calculator, you will see number 7 gives you polar to the x value. Here we put in the magnitude, comma, the angle. And number 8 on that menu gives you the y value. We do the same thing. We plug in the magnitude, comma, the angle in degrees, and we get those values. So your calculator will do these translations from one notation to the other if you want to use that. Write each vector in the figure in the form AB. So here we're just trying to convert, like for example, U is a magnitude of 5 and it's 60 degrees. So we're just going to convert each of these into rectangular coordinates. Instead of polar coordinates, magnitude 5, angle 60, we want it in terms of x and y. Okay, U cosine theta, U sine theta. And so here we get 5/2, 5 over the square root of 5 square roots of 3 over 2. I'm not going to go through a lot of this, okay? I mean, you could have put them in decimals, etc. There's B, -2, 0. And you could have seen that even from the graph. And C, 1.04, -5.9, etc. Again, I'm not going to go through these. These are pretty simple calculations. Hopefully that wasn't a big deal. But now let's see what happens. Oh, sorry, nope. Wrong slide. Let's look at some things that happen between that we can do with this rectangular notation that's really cool. So notice, remember when I add two vectors, I get a resultant vector, which was that the diagonal of a parallelogram, or the triangle that's formed by, putting them end to end and then connecting it. Well, notice if they're in rectangular form, I can find the coordinates immediately of the resultant simply by adding the x values and adding the y values. And then I could easily convert it back into polar form to find, angles, etc. Okay? Here we have scalar multiplication. If I'm trying to do 2 times a vector with x and y format or the rectangular format, I just multiply the x by that scalar number, 2 or 1/2 or whatever, and also do that by y, and that gives me my new vector. If I want the negative vector, the opposite direction of the vector, I just multiply x and y by a -1. And if I want to subtract, I just multiply the second vector by -1 and then add it, or do the x1 minus x2, y1 minus y2. We just subtract those. Okay. So those were pretty intuitive things. Again, we're just going to add x's and y's for u plus v. We're just going to add the x values and the y values. Actually, let me stop there. Again, it's a good idea. Why don't you hit pause, see if you can do these 3 simple problems, and then hit play again. So hit pause, try these, and then move on. All right, for A again, we're going to add the x values. -2 plus 4 is +2. 1 plus 3 is 4. And so we get 2, 4. -2u is simply multiplying u times -2, multiplying the -2 times the x and the y. Oops, sorry. Excuse me. I moved on too fast. I wanted you to be able to see the diagram for A. So there you have u, there you have v. This is the resultant vector that we could have created by using the parallelogram. Okay? For B, as I mentioned, we're just going to multiply x and y by -2, and so we get 4, -2. And here we can see that that really does work out. Here's u, here's -2u. It's directly opposite direction, and it's twice the length or magnitude of u. 3u minus 2v, this is a little bit more involved. So first we're going to multiply vector u times 3. We're going to multiply vector v times 2, which just, of course, means multiplying each of those vectors, x and y values. And then we're going to subtract those new x and x values from each other and the y values as well. So first we multiply u by 3 and v by -2, or by 2. We get 3 times -2 is -6, etc. Then we're going to take the x values, -6 minus 8, the y values 3 minus 6, and we get -14, -3 for our resultant vector after this operation. This is a much more involved operation. So you can see here we've got a number of things. We've got first 3u, we've got 2v, and then of course -2v, and then you've got the resultant vector there. All right, so this makes vector calculation or resultant calculation much simpler to find that resultant vector on a graph. Another thing that we can do, and this actually helps us with something called the dot product, is we can state vectors in terms of unit vectors. And the idea here is that vector I is simply a vector along the x-axis with a magnitude of 1. Okay? Vector j is a vector along the y-axis with a magnitude of 1. So I kind of represents the x vector, or the horizontal vector. J represents the vertical vector. Okay? So if I have a vector u that is equivalent to 3, 4, I can also write this as a unit vector, which is the x value times I plus the y value times j. Okay, so it's 3 of the unit vectors of x, which is, what we know about graphing, and 4 of the unit vectors of y. And so it's just another notation for vectors that helps us solve some specific problems. Okay, again, here we just take the x value times I plus the y value times j. All right, so this is where this can kind of help us a little bit. If we have two vectors in rectangular format, that's the xy coordinates notation. If we see u times v with a little dot in between, we read this as actually u dot v, okay? And we do this because it has a very specific type of multiplication that's a little bit more similar to matrix multiplication. And it's given by multiplying the x values and adding those to the product of the y values. So multiply x's, multiply y's, and add them together. You see that? That's the dot product. Multiply x's, multiply y's, add them together. Multiply x's, multiply y's, add them together. So again, hit pause and try these two problems to kind of get just a little bit of experience with the dot product. And in a minute, we'll explain why we want to know this. So again, multiply x's, multiply y's, and add them together. Hit pause and try these two. So for A, we have 2 times 4, the x values, 3 times -1, the product of the y values. When we add these together, we get 5. For problem B, we get x6 times x -2, plus y4 times y3, and when we add these together, we get 0. Okay? Dot product, very simple to find. Okay? And what are some properties? Dot product works pretty much like all other multiplication. It is commutative. It doesn't matter the order that you put them in. It is distributive. So if I have u times v plus w, it's uv plus uw. It is, this is commutative again. It's commutative, I don't know, I guess you would say this is distribution commutative. It doesn't matter the order. Okay. It also is associative, that you can group different elements together and multiply them first, just like 2 times 3, then multiply by 4 is the same as 2 times the product of 3 and 4. And if we times it by 0, of course, we're going to get a 0 magnitude. And if we times it by itself, we're going to get that magnitude squared. All right. So here's where we get the geometric interpretation of the dot product, and that is, how does the dot product relate back to the angle? Okay. The angle specifically between two vectors. This is, again, you think of when you're talking about the resultant. What is the angle between two vectors? So if we take the dot product and divide it by the product of the magnitude of each of the vectors, if we take the dot product and divide it by the magnitude of each of the vectors, the product of the magnitude of each of the vectors, this is equivalent to the cosine of the angle between them. Okay, add this to your notes and use this. Okay, so if we want to find, again, hit pause and do this problem. Find the angle between the two vectors. It's very straightforward. You're going to need to find the magnitude of each vector, which we did earlier in this lecture. That's the denominator. The product of both of those magnitudes is the denominator. And the numerator is the dot product, which we just did, the x values product plus the y value product. Okay, hit pause, try these, and then hit play. So in the numerator, we get x's times y's. I'm sorry, that is not true. That's the dot product of 3, 4 times 2, 1. They just rewrote it in rectangular form. And then we need the magnitude of vector 3, 4 and the magnitude of vector 2, 1. Okay. Well, in the numerator, we get 3, the x value product, 3 times 2, plus the y value product, 4 times 1. Remember, the magnitude of each vector is equal to the square root of the sum of the squares of both the x and the y values. So we get 3 squared plus 4 squared, the square root. 2 squared plus 1 squared, the square root. Okay? This simplifies to 10 over 5 square roots of 5. And so again, remember, this is the cosine of theta is equal to this, so we need to do the inverse cosine of theta. Now you've got to be careful, all right? If you plug this into your calculator in this way, you'll probably get an error, because what's going to happen is your calculator is going to say the inverse cosine of 10 divided by 5, and then it's going to try to divide all of that by the square root of 5. Okay? Even though this is all in one parenthesis, which kind of confuses me a little bit, why it reads 10 divided by 5 times square root of 5. Well, 10 divided by 5 is 2, right? The inverse cosine of 2 is undefined, so you get an arrow. It's outside the domain, okay? So you can plug this in your calculator this way, but you really need to put the entire denominator inside the in parentheses inside this bigger parenthesis. So it should be 10 divided by, or slash, left parenthesis 5 square root of 5, right parenthesis, and then of course parentheses after everything. Okay? Another way you can do this is kind of doing this whole division problem first, again putting parentheses all around the denominator, and then taking the inverse cosine of that answer. It's really easy to mess these up when you have these complex products in the denominator, where it gets confusing, like why you're getting an error on your calculator. Okay, so let's do one more of these. Again, I'm going to suggest you hit pause and then go ahead and solve this. So I'm going to move forward. We know that the cosine of theta is equal to the dot product of u times v over the magnitude of u times the magnitude of v. And again, the product of the x's, 2 times 6, the product of the y's, negative 6 times 2, over the magnitude of 4 plus 36, 2 squared 4, negative 6 squared 36, 6 squared 36, 2 squared 4, okay? And we get 0 over 40 equals the cosine of theta, okay? So the cosine of what angle equals 0? That's 90 degrees. You could have done the inverse cosine, but hopefully you also knew that as well. Okay? So when you're looking at the dot product, some things can come out immediately. When you do the dot product, if you get a positive number for the dot product, then your angle is going to be acute, right? It's going to be in quadrant 1. It's going to be between 0 and 90. As you saw in the last problem, if the dot product equals 0, you're going to get a right angle. And that goes with this note down here. So if the dot product of u and v is 0, then the cosine equals 90. I'm sorry, the cosine theta equals 0, and theta will equal 90. Thus, u and v are perpendicular, which of course is what happens when you have a right triangle, or a right angle, right? That they're perpendicular or orthogonal. Orthogonal is another vocabulary word we use for perpendicular lines or vectors. And then if your dot product is negative, you're going to have an angle greater than 90 degrees or obtuse. All right, so this ends chapter 7. Hopefully this has helped you, and good luck on the test.